Hey everybody. Today we're doing an example computing a confidence interval for the mean in a situation where the population standard deviation sigma is known to us. Suppose we have a bathroom scale and readings on it are going to be normally distributed with mean equal to the true weight of the person being weighed and standard deviation of 0.8 kilograms. By the way, I know that kilograms are a unit of mass, not of weight. Thank you for understanding that I'm just going to be a little loose in my speech during this video. Now, individual results from weighings can differ substantially from the true weight of a person. By the empirical rule, an individual weighing will be off by at least 0.8 kilograms, one standard deviation, about 32% of the time, because about 68% of the time the weighing will be within one standard deviation of the mean. If we want to get a more complete picture of the person's actual weight, we should weigh them repeatedly, find the sample mean, and then compute a confidence interval using the formula mu equals x bar plus or minus z star sigma over the square root of n. Here, x bar is the sample mean of our observations from those repeated weighings. Z star is the critical z-score associated with the level of confidence c, and n is the sample size. Of course, sigma is the population standard deviation, 0.8, that was given to us as part of this problem. So we get the critical z-score just using a table most usually. We're going to use the most common confidence level, 95%, which has a corresponding critical z-score of 1.960. Sometimes you'll also see 90% or 99%. The critical z-scores are shown in this table here. If you have a different confidence level for some reason, you have to resort to using an inverse cumulative distribution function for the normal distribution. We aren't dealing with that at all right here. So suppose we weigh this person 5 times and we obtain a sample mean of 77.2 kilograms. Then a 95% confidence interval for the mean is going to be given by 77.2 plus or minus 1.960, that's the critical z-score from the table that we had on the last slide, times 0.8 over the square root of 5. 0.8 being the population standard deviation, 5 being the sample size. We simplify that, we get 77.2 plus or minus about 0.7 kilograms. So our point estimate is 77.2 kilograms. If we had to give one number that was our best guess at the person's weight, we'd say 77.2. The margin of error is 0.7 kilograms. That quantifies the uncertainty in that point estimate. By the way, the interval 77.2 plus or minus 0.7 can also be written 76.5 to 77.9. So there I've literally just subtracted 0.7 from 77.2 to get 76.5 and then added it to get 77.9. Now, bear in mind that the uncertainty in a confidence interval comes from the random sampling process, not the parameter. So the person's true weight in this example is not a random variable. It's not random. It's just unknown to us, and those two things are pretty different. So it would be wrong to say there's a 95% chance that the person's true weight lies in this interval. A better way of explaining what this confidence interval means is to say that 95% of the time, the process used to create the interval will capture the true weight of the person being weighed. In other words, if we go out and do another 5 weighings and make another interval, do that again, 95% of the time, the person's true weight will be contained in that interval.